attendees. So maybe we can wait a few more minutes for start. So now in this session, we will have student presentations. In the meantime, maybe I can check with you. Let me just a moment, please. Where's my... Okay. Okay, let me check if people are here. Mario Cirillo.
Yes, here I am.
Okay. Hello. And Jose, are you here?
Yep.
Perfect.
Here.
Okay. Amedio?
Yeah, here.
Perfect. Murat Esendemir? Murat Esendemir? No. Okay. So in the meantime, I can make Mario co-host. Why I don't see him?
I think that somebody just made me co-host this morning by mistake, but okay.
Yeah, you are a co-host now. Okay. So maybe you can share your screen in the meantime before start.
Okay. Can you see the whole presentation?
See.
Okay.
Da Roma.
Yes.
Perfetto. 19 people. Okay, one more minute, then we will start.
Okay.
Okay, Mario, I think you can start. Everybody will have 10 minutes. Please try to be in the time. So please go ahead.
Okay. Good afternoon, everybody. I am Mario Cirillo, and I'm a third-year PhD student from Italy. I come from Rome, from the University Tor Vergata, and from the National Institute of Astrophysics in Italy, in Abruzzo. My talk will be about evolution and nucleosynthesis of extremely metal-poor stars. Population tree stars are the first generation of stars, and they have zero metals. They only have hydrogen and helium. However, they are important for two main reasons. The first, because they are the most likely energy sources for the reionization of the universe. And then because they provide the first nucleosynthesis of elements heavier than helium. When these stars die, they enrich the intergalactic medium with their chemical ashes, and subsequent generation of stars will form from the ejected material. However, they have not been directly observed yet, but there are some observational constraints on their existence, such as detection of metals in Lyman alpha for spectra of distant quasars, or detection of metals in damped Lyman systems, or abundance ratios in extremely metal-poor stars, so stars which have an iron over hydrogen ratio less than -3. So it is crucial to study the nucleosynthesis and the evolution of these stars. My talk will focus on models of extremely metal-poor, low and intermediate mass stars with masses between 0.8 and 8 solar masses, with particular attention on their evolution and nucleosynthesis. So I will present three models with mass 6 solar masses and different metallicities, 10⁻⁴, 10⁻⁶, and 10⁻⁻10. and one model with mass 2 solar masses and metallicity 10 to the minus 5. The main thing of these models is that we adopted a full coupled code with an advective mixing scheme. And a full coupled code is extremely important in order to follow the evolution and the nucleosynthesis more precisely, especially during the AGB phase. As far as the models with mass 6 solar masses and different metallicities are concerned, I report the mass of the cores at each convective episode during the central hydrogen burning and the central helium burning as a function of time for the three models. We can see that there is a progressive reduction of core masses at each convective episodes. So we deal with more and more compact structures. Moreover, we can see that for the first two models, we have two convective episodes corresponding to the onset of the CNO cycle, so a receding hydrogen core, and to helium burning, so an advancing in mass hydrogen helium core, as we would expect in higher metallicity stars. However, in the stars with the lowest, in the star with the lowest metallicity, 10 to the minus 10, we can see that there are three convective cores. This happens because due to the scarcity of metals, the stars burns hydrogen through the PP chain. So the CNO cycle is only partially activated and a first convective core is established. Then the star contracts until it reaches the temperature of 10 to the 8 Kelvin. And 3 alpha reactions takes place producing carbon. When enough CNO is produced, more specifically when its central abundance is 1.8 times 10 to the minus 10, the CNO cycle is activated and the second convective episode appears. So the peculiarity of this model is the coexistence of a phase in which central hydrogen burning and central helium burning are burning together. And then we have the third phase, which is the core helium burning, as in more metal-rich stars. This leaves a footprint in the Espelon-Russell diagram, as we can see in the circle. Moreover, these stars are hotter than metal-rich stars, so we can also see in the Espelon-Russell diagram that helium burning takes place in the blue part of the diagrams. Regarding the model with mass 2 solar masses and metallicity 10 to the minus 5, there is a proton ingestion episode at the beginning of the thermally pulsing AGB phase. This is a new phenomenon which is not present in more metal-rich stars, and then I'm going to explain why does it happen. During this phenomenon, the hydrogen shell reaches a luminosity which is 10 to the 10th solar luminosity, so a very high luminosity. And after the subsequent third dredge up, all the surface main CNO abundances are raised to surface and from 1 to 3 orders of magnitudes. But let's see what happens at the start during a proton ingestion episode. During the thermally pulsing AGB phase, the stars has two shells, the helium shell and the hydrogen shell. And when a thermal pulse occurs, a convective zone forms in the helium shell, above the helium shell. And due to the fact that the hydrogen shell represents a lower entropy barrier in these metal pool stars, if the helium convective zone generated is large enough, it may penetrate the hydrogen shell and take protons from the envelope, bring them down and burn them at higher temperatures. So in this video, I will show what happens. More specifically, this video shows the radiative gradient in black and the adiabatic temperature gradient in red. And convective zones are individuated by means of the Schwarzschild criterion for convective stability. So where the radiative gradient is larger than the adiabatic one, we have a convective zone. This is the helium shell, which is convective, and this is formed after the thermal pulse, and this is the convective envelope. So we can see that the helium shell is advancing in mass and is approaching the convective envelope. And then when protons are brought inside, there is the splitting of this convective zone in two different convective zones. The most internal, in which the 3 alpha reactions takes place, and the most external, in which the CNO cycle is activated. Then we have the disappearance of both the two zones and the third dredge up, which brings to surface the products of this phenomenon. So in this plot, I show the internal mass, the main surface abundances of the CNO cycle as function of the internal mass coordinates in 3 different situations: before the proton ingestion episode, when the proton ingestion episode is at its maximum luminosity, and after the third dredge up has occurred. The blue dashed area represents the helium shell. The green hatched area represents the convective zone, which is generated after the proton ingestion, and the orange squared pattern is the convective envelope. Before the proton ingestion episode takes place, in the convective zone generated by the thermal pulse, 3 alpha reactions takes place and carbon and oxygen are produced. After the ingestion of protons, the formation of a second convective zone, we witness the formation of a second convective zone, and the CNO cycle is activated. So all these, all its main components are raised in abundance. Finally, we have the penetration of the convective envelope, and we have a surface enrichment in the main CNO isotopes. Finally, I also analyzed the lithium-7 production in this star, and I plotted the lithium-7 abundance in black, the beryllium-7 abundance in red, and the boron-11 abundance in blue. Before the proton ingestion episode takes place, boron-11 is produced via alpha captures on both lithium-7 and the beryllium-7. Then, after the ingestion of protons, beryllium-7 is produced via alpha captures on helium-3. And we can see also that lithium-7 starts being produced by electron captors on beryllium-7. This happens when the temperature is almost below about 20 megakelvin. Finally, we can see that all this beryllium-7, which is produced in the green area, is brought to surface by the following third dredge up. And due to the fact that electron captors on beryllium-7 are enhanced when the temperature is low, all this beryllium goes into lithium. So surface lithium mass fraction grows from 10 to the minus 13 to 10 to the minus 8. So for 5 orders of magnitude. This is my conclusion. So I analyzed 3 different models with mass solar mass metallicity 10 to the minus 4 and 1 model with mass to solar masses and metallicity 10 to the minus 5, using a full coupled code with an advective mixing scheme. I report here the main findings of the 4 different models, and I stress on the surface enrichment in CNO isotopes and large surface lithium-7 growth in the last model. And the future activity is a full grid of extremely metal pulsars models with different masses and metallicities in order to investigate their main properties and anomalous phenomena such as the proton ingestion episode. Thanks to you for the attention.
Thank you, Mario. Is there any question for Mario in the EMP stars? Okay, we can maybe go fast. Thank you again. Grazie.
You're welcome.
Jose?
Yep.
We can start sharing.
I'm here. Yep. Yes. So can you see my screen?
Yes, we can make full screen. Perfect.
It's working.
Perfect.
Okay, hello, everyone. First of all, I would like to thank you for this wonderful tool. I'm a PhD student at University of Padua, and today I'm going to talk about lithium abundances as a tracer of the vulnerability of second generation stars in the global cluster NGC 6752. But first, let's start with a brief introduction. So, as you know, spectroscopy is an excellent tool to study in detail the composition of the stars, which is critical to shed light on the multiple star population phenomenon. For those who are not familiarized with the topic, very briefly, in a global cluster, we can find different star populations. First population, which is made from the pristine gas. And a fraction of these first generation stars are going to pollute the cluster with the elements processed in their interiors. And after a while, a second generation of stars are going to be formed from the mixture between the pristine gas of the cluster and the polluted gas from the first generation stars. And obviously, as you can see from this scheme, the chemical composition of these two populations are going to be different because they are made from different materials. So while this phenomenon is well known, the nature of the polluter is still under debate. So there are several potential polluters, such as fast rotating massive stars, binaries, intermediate mass HB stars. And we think that analyzing the lithium in these different populations can help to understand better the nature of the polluter in this cluster. So we analyzed more than 200 stars from the archival data, and all these stars are located between the turn off the cluster and the bottom part of the RGB. And we synthesize both the lithium line and the aluminum line. So here you can see some results, and they are part of a paper that was just submitted to the journal. On the left, we can see the aluminum abundances as a function of log G, and as you can see, most of them are dominated by upper limits because we could only report aluminum abundances when the line was strong enough to be measured. But anyway, as you can see from the histogram on the right, we found a continuous distribution rather than a multimodal distribution, meaning that we didn't find evidence of multiple episodes of star formation. On the right, you can see the lithium abundances as a function of log G, in pink stars here, and also the pink dashed line indicate the prediction or the predicted lithium abundances by models. As you can see, or as we could expect from the stellar evolution point of view, we can see that both the models but also the observations shows an overall decrease of the lithium abundance from the turn off to the bottom part of the RGB. So here you can see the lithium abundances as a function of aluminum. In the upper panel, you can see the results for unevolved stars, and in the bottom panel, you can see the results for evolved stars. The vertical line here at aluminum abundances equal to 0.4 split the sample in first and second generation stars. What we expected to find here was an anti-correlation between these two elements, with the first generation with high lithium but low aluminum, and a second generation with low lithium and high aluminum. But what is interesting here are these stars there They are second generation stars, but with high lithium. And this is telling us that some production of lithium is needed. So the polluter responsible of the pollution in this cluster must be able to produce lithium. So according with models, the only lithium nucleosynthetic site is the interior of AGB stars. So they must be involved in this phenomenon, at least in this cluster. So moreover, AGV stars also produce some S-process elements, and their production depends on the mass of the AGV star. So by studying the lithium-rich and lithium-poor population as a function of neutron capture elements, we can constrain a little bit more the nature of this polluter. And here you can see a preliminary result, which is going to be part of a second paper, where I'm showing differential analysis between two giants with similar stellar parameters and moderate different lithium abundances. And this analysis showed a slightly higher barium and yttrium abundances in the lithium richer star. Unfortunately, we don't have more pairs of stars to do this kind of analysis, but we aim to do a fully characterization of neutron capture elements in UV spectra to constrain the mass range of the polluter of this cluster. And this is my last slide. I don't have more time, but I just want to remind you that a detailed paper about this work will be available soon on ADS and archive. So keep an eye on this. Thank you.
Thank you, Jose. Is there any question?
I have one.
Please go ahead.
These lithium-rich stars that you find, that you assume should be second-generation stars, if I have understood.
Yeah.
No?
Yes, yes.
Okay. You find this enhancement of typical S process like yttrium and barium, but they are also enhanced in neon and aluminum?
Actually, we are working in the S-process elements analysis and other proton capture elements also. For the moment, we just analyze lithium and aluminum, but we are working on more elements. So I cannot tell you that now.
Neon is enhanced in this lithium-rich star? Neon.
Sorry?
Neon.
Yes, sorry, what was the question?
The question is if neon is enhanced.
We didn't analyze yet neon, so
okay.
I can tell you that
okay.
for the moment, sorry.
Okay, sorry. Thanks.
Okay, thank you, Jose, once more. So the next speaker will be Amadeo.
Yes, here.
Please share your screen.
Sure. Okay, let me just see how to do it. Right. Okay, can you see it?
Yeah.
Okay, awesome. So, hi everyone. I'm Amedeo Romagnolo from the Nicolaus Copernicus Astronomical Center in Warsaw, Poland. So today I will talk about the crucial importance of the radial evolution for stars in order to get compact object mergers detections with LIGO and Virgo through gravitational waves. So to begin with, let's just have a little understanding of how gravitational waves are produced.
Amadeo, do you present on your cell phone, smartphone?
No, why?
Okay, the view is a bit strange, but it's okay. Please go ahead. I don't want to interrupt.
Okay, sorry. I will try to make my microphone closer.
Because the screen seems like empty in the vertical parts, but it's okay. It's
well, yes, it's just that I have a vertical monitor. Sorry. Okay.
I see. No, it's okay. Go ahead.
Okay. Okay. So what I was saying. Okay. Yes. So we need to have gravitational waves, first of all, through compact objects defined as either neutron stars or black holes that are converting their orbital energy into gravitational waves until they eventually merge and coalesce into a bigger compact object that is likely a black hole that is probably, so far, for as far as we know, gravitationally stable and doesn't product gravitational waves anymore. So to get a compact object, we essentially need a massive star that, well, we have some uncertainties in some mass ranges, but in general, we need a star whose initial mass is beyond 8 solar masses to get a compact object. But of course, as I mentioned before, we just don't need one compact object, but we need a binary compact object. So we need to have a stellar system, a binary stellar system, which will then evolve into 2 different compact objects orbiting around a common center of mass. And for these compact objects to be detectable through gravitational waves, they need to be massive enough if compared to their distance from the observer, and they need to be close enough for us to detect them, because the major point here is that the closer these compact objects are to each other, the more energetic and therefore more luminous the gravitational waves radiation will be. So to get this orbital separation, we must include the binary physics in our considerations, and in particular, the interactions between the 2 stars. One of the most crucial events that we need to consider for binary interactions are mass transfer events. So a mass transfer event happens when one of the 2 stars increases in size and goes beyond a specific limit that is called a Roche-Loeb radius. Beyond this point, its stellar envelope will start getting accreted by its stellar companion. So if the accretion is unstable, the envelope will not only be accreted, but it will surround for a certain period the whole binary system and create what is called the common envelope phase that you can see in the bottom left panel. So either the stable mass transfer or the common envelope phase face a crucial phase in general that mainly the major point here is that the stellar envelope is not only accreted, but part of it is dispersed as well. So if you are getting some mass of the binary system, you will also lose some angular momentum, and therefore your orbital separation will decrease. On top of that, in the common envelope phase, the envelope also creates friction between the 2 stars, and therefore it further decreases the angular momentum, because it converts orbital energy into thermal energy. But the major point here is that even if we had a complete understanding of mass transfer events, and we don't, a huge source of uncertainty will be the evolution of massive stars, and therefore how big they can get, and if they can then overflow the Roche-Loeb. As you can see in the plot on the right, which shows the maximum radius that a star can obtained throughout its whole lifetime in function of its initial mass, different theoretical models predict different radial evolutions, and these models could differ even of order of magnitudes. This means that if we use different models, we create different compact object mergers, and therefore we increase or decrease the likelihood of mass transfer events to start. So you can see on the table on the left, for instance, that I did my own calculations on how likely compact object merger is to be detected by LIGO-Virgo observations with these three different models, with Hartley as the unconstrained radius rho. But essentially the point is that by decreasing the maximum obtainable radius, you're also decreasing the detectability of compact object mergers. So to conclude my talk, the major point here is that there are huge uncertainties of one of the major factors for gravitational waves astronomy, which is the radial evolution of a star. If we can understand the general evolution of massive stars and therefore their radii, we can really better understand the whole gravitational waves astronomy. But in order to do that, we need to further constrain our models with more gravitational waves observations and more accurate observations in the electromagnetic spectrum. And with that, I thank everyone, and we're over.
Thank you for a nice talk. Is there any question for Amedeo? Amedeo, are you working in the Virgo or LIGO consortium?
I'm not a member of the Virgo LIGO consortium, but my work is mainly on LIGO and Virgo observations, yes.
Okay. So if there's no question, thank you, Amedeo, grazie.
Thanks to you.
So we can continue with, I think Murat is not with us, so we can continue with Beatrice.
Yeah,
Good.
hello, can you hear me?
Yes, we can hear you.
Okay, very good. I'll share my screen.
And then here.
Okay. So hello everyone, I'm Beatrice Giudici and I'm a PhD student in the University of Valencia. And today I'll tell you something about long-time supernova simulations. So first, let me do a brief introduction. So we know that stars with masses between 12 and 30 solar masses develop an onion shell structure, as heavier elements are produced via nuclear fusion. And we have lighter elements outside, and then heavier elements up until the iron core. However, when nuclear fusion reactions cannot balance the gravitational contraction, the star begins to collapse. And the supernova explosion is triggered. However, if we rely only on the energy released during the explosion, we discover that the shock wave will travel for about a few hundred of kilometers. So we need another source of energy in order to permit to the shock wave to go further. This energy is brought by neutrinos via the delayed neutrino heating mechanism, theorized first by Wilson and then so with simulation by Wilson and Bethe in 1985. This theory was proved also by an observation that happened 2 years after their publication. That is the observation of supernova 1987A. And here you can see a little ID card of the supernova. So this observation was very important for many reasons, but first because it was the first direct detection of neutrinos coming from a supernova explosion, and was detected by 3 different experiments, Kamiokande 2 in Japan, IMB in the US, and Baksan in Russia. So this event marked the beginning of neutrino astronomy. However, due to the fact that it was detected in a modern era where lots of computers are used for research, it brought a huge amount of new data for calibration of simulations. And moreover, it dismantled a belief that supernova explosions were spherically symmetric. In fact, up to that time, the scientific community believed that supernova explosions were mainly spherically symmetric. However, this observation brought the evidence that strong hydrodynamical mixing processes and instabilities, such as Rayleigh-Taylor instabilities and others, have a role from the very beginning of the explosion. And this caused the supernova to be not spherically symmetric in principle. As you may have read before, the progenitor of supernova 1987A was a blue supergiant star. So the next years, the work of the next years was focused mainly on blue supergiant stars. There are a lot of work on simulation about that. However, we know that there are also red supergiant stars. So my project is focused instead on supernova with progenitor a red supergiant star. In order to do so, I use a code that is called Prometheus that was developed in the early 90s. And here you can see some technicalities, but I won't spend time on that. The preliminary study for my simulation was a 1D explosion. And I take a subset of the huge sample brought by Azarquiel et al. And I consider 7 progenitors with masses between, these are zero age mean sequence masses, between 12.5 and 27 solar masses. And I try to have similarities between super results and mine. The domain begins at 350 kilometers because we are focusing on the outskirts of the explosion. So we model everything that is below 350 kilometers as a point mass in the center of the coordinate system. And here you can see some results of, this is the case of model 19.8 solar masses. So you can see that there is an explosion at about 0.3 seconds in the simulation. And the explosion energy rise up until a plateau at a few seconds in the simulation. And the same behavior is mimicked by the mass of the nickel. Here in red, you can see that it begins to grow up until a plateau. And also in blue, I plotted the mass of the nickel plus the tracer. This tracer is just a fictitious element that helps in calculation of nucleosynthesis. However, we believe that nickel plus tracer is a sort of upper limits for the nickel production in supernova. So after that, I moved to 3D simulation. So I took the same radial component and I added the angular components. These means that we have resolution of 2 degrees in both angular directions. And here I plotted some results of the same model as before at a time t equal to 2 seconds. You can see that even at these early times, we have some deviation from the spherical symmetry, for example, here along the x-axis and also a little bit on the top. And this is on the left, you can see the reproduction of the entropy per baryon that is mimicked by the mass of the nickel on the right. So the aim now is to prolong the simulation further and further, even for many days or months after the explosion, in order to see how beta decays can affect the distribution of the mass. However, the simulations are running as we speak, so I am not able to present my data, but I want to just have a quick example of what we expect to see. In particular, these are 2 models run by Wongwatana et al. In 2015, and you can see on the lower row a 20 solar mass star that is evolved up until 6,000 seconds. And you can see that it presents a more or less spherical symmetry at the beginning that is maintained through the simulation. Instead, on the upper, we can see a 15 solar mass star, where some deviation from spherical symmetry are developed in the early times. We speak about 2.5 seconds in the simulation, and these are evolved up to thousands of seconds. However, these are just blue supergiant stars. So in order to conclude, we observe that supernova explosions are affected by hydrodynamical instabilities from very early stages after the explosion. And so we have a deviation from spherical symmetry. And this was discovered with the observation of supernova 1987A. And it also helped set in the parameters for numerical simulations. However, red supergiants are yet to be extensively studied. So we aim to give a large sample of red supergiant supernovae, both for understand how they behave, but also to compare the results with the observational community in order to understand better the nature of supernovae. And I thank you for your attention.
Thank you, Beatrice. Is there any question? With these energetic events. So are you comparing, besides the simulations, are you also taking into account the observed supernova remnants, like, I mean, besides the S87A?
Yes, actually, for the lower mass star, here for the 12.5, it is believed that it's more similar to the Crab Nebula, to the Crab supernova. So in the literature, there are just supernova 1987A and Crab for lower mass stars.
But I mean, when you say it's not spherically symmetric, because when we look to supernova remnants, we may be affected by some projection, for instance, projection effects. So how do you take into account this? And from the, I mean, do you say when it's when they are not spherically symmetric, do you mean by the simulation results, or also you can compare with some observational remnants? That's why what I'm asking.
No. The observation of supernova 1987A proved that in general, I mean, that there could be the case where supernova explosion are spherically symmetric, but also it was proven by observation, and of course it's easier to see that in simulations, but we expect to see that also in observation.
Okay. Our attendees are very silent, very quiet. People don't ask questions, don't speak. Okay, maybe the online environment is that. Thank you, Beatrice, again.
Thank you.
And now Elena, I think she's here.
Yes, I'm here.
Okay.
So you can see my slides.
Yeah. I mean, we are seeing your screen, but not the slides. I think you have two screens.
No, I don't have. You cannot see the slides?
We have, okay, we see the timetable, actually. Azarquiel timetable at the moment. Is it your screen? Yes, Elena, yeah, it is yours.
Yes.
Maybe stop share and start again, and choose the window if you like. Choose the whole screen, not the specific window, if you want.
I don't know if.
Yeah, that's okay. Now it's okay. Perfect.
Is it okay now? Okay. Perfect. So good afternoon. Today I'll present my work regarding the role of type 1a supernova feedback on the second generation formation in globular cluster. So globular cluster are old and complex stellar systems that are orbiting the Milky Way, but also external galaxies. From the chemical point of view, we have that most of the stars that they host are very metal poor stars, and the bulk of globular cluster are found to be monometallic, so the dispersion in the iron over hydrogen ratio is found to be lower than 0.05 dex. But the most unique and peculiar feature regarding globular cluster, and as also Jose mentioned, is that they show anticorrelation in their light element abundances. Here you can see some of these anticorrelations that has been observed. The most famous one is this one, that is the sodium oxygen one. And these anticorrelations are now accepted to be caused by the proton capture reaction and hydrogen burning at high temperature. These reactions are taking place inside, obviously, these stars. And now we know that it's widely accepted that these anticorrelations are causing that globular cluster underwent self-enrichment. So we can either speak about multiple populations, but also about multiple generations. So we have that stars inside globular clusters are not born at the same time, but in subsequent generations of subsequent births of star formation. Now there are different scenarios for the formation of globular cluster. The most widespread one is the asymptotic giant branch scenario, in which second generation stars form from the ejecta of third generation stars. However, since with AGB ejecta only, we are not able to reproduce the second generation abundance patterns, the AGB scenario has to assume also dilution of these ejecta with pristine gas. Here there is a nice sketch regarding the formation of a globular cluster in this scenario. So we start with a first generation that is a first generation of stars that is located in the disk of a star-forming high redshift galaxy. Then core collapse supernovae start exploding and they carve a hole around the cluster. Then this hole reaches the height of the disk and all the and then there's a blowout. So all the ejecta of core collapse supernovae are assumed to be left into space. Then once core collapse supernovae stop exploding, the bubble collapses, and we are at this stage here. But as I told you, the asymptotic giant branch scenario is one of these scenarios for the formation of globular cluster, and as many others, it has also some problems and still open questions. And one of these is what has halted the star formation of the second generation. Here we have that in the AGB scenario, generally type 1 supernovae are assumed to halt the star formation after some 100 mega years. This is based on the results found by Azarquiel 2008, who performed 1D hydrodynamical simulations for a massive globular cluster. And here you can see the differences between the models with and without type 1 supernovae, which are starting in this case at around 40 mega years. So once supernovae start, the star formation rate drops almost immediately. And what we wanted to investigate is if it is really so also in 3 dimensions, and in particular to see if which are the side effects due to type 1a supernovae, for example, their effects on the chemistry. So we started from this step here. So once core collapse supernovae has already stopped exploding, and the system is composed just of low and intermediate mass stars. The most massive ones are undergoing their AGB phase. And then we're assuming also that the cluster is orbiting its host galaxy. So we have an asymmetric accretion of pristine gas from one of the boundaries. And we added type 1a supernovae to this setup. So just to give you some numbers, I'm modeling hydrodynamically a globular cluster with a first generation of 10 to the 7 solar masses distributed following a Plummer profile. In the time span we were interested in, that was about 100 mega years. We have around 1,000 supernovae 1A that are exploding, and I tested 2 values for the pristine gas density, that is the ISM density of the host galaxy. So for each supernova, in the code, we inject almost a Chandrasekhar mass of metals, out of which 0.5 are in iron and 10 to the 51 ergs of thermal energy. So going to the results for the low density case, so for density of the ASM of 10 to the minus 24 grams over centimeters cube, we have that the inflow of the pristine gas starts at around 21 mega years, and it comes from this boundary here. But as you will see, the inflow is not able to reach the central part of the system. Here you can see it here. And because supernovae 1A are pushing it far from the center, And if we compare with the results obtained by Kalua 2019 for the same model, but without type 1a supernovae, we have that we can see clearly an accretion column formed here that is not present in our simulations because the infall is not able to, the infalling gas is not able to reach this the right part of the system. While for the high density model, so for a density of 10 times greater, we have that the infall starts immediately. Here the situation is different because the infall is able to reach the central part of the system, and because supernovae 1a are not that efficient in blocking it. And the accretion column clearly seen here in the case without type 1a supernovae can be seen, especially if we look at the velocity field displayed by the arrows, but it is continually disrupted by supernova explosions. So then if we go back to answer our questions, so if type 1a supernovae are able to halt the star formation in a massive globular cluster, the answer is that it depends on the density of the pristine gas, so the SM gas. So if we have a look at the low density models, so the blue ones, if we compare the case without type 1a supernovae, that is the thin line, with the case with type 1a supernovae, we have that this last one, so the case with type 1a supernovae, hardly ever reaches the value obtained in the case without type 1a supernovae, and the final mass that we obtain at the end of the simulation is reduced significantly. While if we go to the high density model, we have that there is a very low difference, a small difference, especially at the beginning, but then the star formation rate is almost the same as in the case without type 1a supernovae, and also the final mass is almost the same. Then going to the chemistry, just for a brief definition, globular clusters can be divided into type 1 and type 2 globular clusters. Type 1 are globular clusters that are monometallic, and then there is a subclass, very small, that is called type 2 globular cluster that show an iron spread, and in particular, they are generally found to be quite massive. So here I showed the iron distribution. The histogram represents the composition, the distribution of the second generation stars, while the dashed line represents the composition of the first generation. And as you can see in both these models, we have that the dispersion of the iron over hydrogen ratio is quite large. So it is in agreement with what we observe in type 2 globular clusters. And here on the top panel, we can I just show you 2 MDFs for 2 of these type 2 globular clusters for comparison. But the problems arises when we have a look at helium, because in this case, we have that in the low density model, since there is no inflow of gas, we have almost no dilution of the AGB ejecta. So we end up with a second generation that is composed by extremely helium enhanced stars. So if we compute this quantity, that is the enhancement of the second generation with respect to the first generation in the helium mass fraction, we end up with a very large number. And if we compare with what we observe, we see that this point here is completely not matching the observations. Only in the high density model, where the dilution is happening, we are matching what we observe. So going to the conclusions, I've shown you that type 1a supernovae are not able to halt immediately the star formation as it happened in one dimension. And in the low density model, we have that supernovae 1a significantly reduce the star formation, but the major effect is that they prevent the inflow of gas. So we end up with almost no dilution and with an observed helium spread between the first and the second generation. While this is not happening in the high density model, where supernovae 1a are not affecting the star formation, they just cause a large helium spread, just iron spread, which is still in agreement with what we observe in type 2 globular clusters.
Thank you. Thank you for a very fast and quick presentation. Is there any questions for Elena?
Elena, in many slides you have shown, in many plots you have you reported a time or a time scale, but the 0 point.
Yeah, the 0 point is like yes, here. I'm starting from this, so every time the 0 point is at around 40 mega years after the beginning of the first generation, of the birth of the first generation.
Okay, okay, thanks.
So yeah, the beginning of the simulations.
Okay, you start when the first generation, the calculation is done after that the first generation is generated, let's say.
Yes,
Already
yes, the
generated.
first generation, we assume that the first generation massive stars has already gone.
Okay.
So we start once we have only AGBs that are polluting. And this is our starting point, is then our 0 point.
Okay. So in the type 1A, because it's quite fast, the onset of type 1A effects. So I suppose you are considering a single degenerate.
Yeah, I'm considering
scenario.
a single degenerate.
So in which only, so the time scale is that of an intermediate mass star, the evolutionary time scale of an intermediate mass stars.
Yeah, I'm taking the Goethe 2005 formulation for the single degenerate scenario. So we have that there is almost no delay. So we start once AGBs start releasing their ejecta, also type 1A supernovae start exploding. Also, we tested a case in which we delayed supernovae 1A of about 25 mega years just to see if there was any difference, especially for the low density case where we have that we don't have dilution. So we postpone the supernovae 1A just to see if the inflow is able to reach the central part of the system, and so to dilute the GB ejecta. But we have that this delay that we impose is too low, too small, because we have almost no difference.
Thanks. Nice job in any case.
Thanks.
Okay, thank you, Elena and Oscar, for the contributions. The next speakers doesn't seem to be here, but let me ask again. Havva Aksaç, she's with us? It seems no. And Yasmin Said.
Yes, I'm here.
Ah, you are here. Okay, I didn't see. Okay, yes, you're here. So Yasmin, you can start. Share your screen.
Okay.
If Havva arrives, we can listen her afterwards.
Okay. Sorry, I'm trying to share it. I don't know.
You couldn't find the big yellow button, share screen button?
Yes, yes, I can find it.
Okay, then you should select your screen.
I'm using a cell phone, maybe.
Oh, maybe, okay, it's not so easy. It's cell phone, I don't know.
Okay, I'm in the setting now, but
Okay. In the meantime, I remind all the audiences, there is the public talk tonight, I mean this evening at 21 or 5 UTC. No, sorry, 6 UTC, 6 p.m. UTC. Is about Ibn al-Haytham, the important people of the optic. So you can, if you are interested, you can follow the talk from the YouTube channel of the school. What's the status, Yasmin?
I don't know. It's supposed to be in the setting, right? In the webinar setting, but I can't find it. Yes. It's supposed to be.
What do you see when you click the share screen button? What do you see there?
I don't have any screen share button. I don't have one. Only I have webinar setting and chat.
Is it not possible to use a computer? Why you?
Unfortunately, no.
Not at the moment.
Okay, just give me one more minute. I will try.
Okay, can you email me your presentation? Do you have?
Yes, it's a
So
good idea.
I can share it for you, and I can help. I can assist you. Can you
Yes,
email
it
me?
would be very useful. Thank you. I email it on the contact mail of the school.
Just a moment. Where is? Just a moment.
Maybe you can type it in the chat.
I do it. Just a moment.
Okay.
Okay, you got my email now. If you send it to me,
okay, just a second.
I can immediately help you. So it seems that this is gonna be our last talk, Yasmin, because there is no Hawa at the moment.
Do you? Yes, sir.
Just a moment. Not arrived yet. Probably in a minute.
Okay.
Yes, I got it. I got it. Now I open it. I do this. Just a minute. Okay, Microsoft PowerPoint. Share. So I guess everyone sees now. This is Yasmin Said. Go ahead.
Okay. My name. Hello, everyone. My name is Yasmin Said, and I am gonna to talk about solar proton flares. My talk will be partially based on a research paper. Proton flare triggered the MW 8.1 Chips Mexican earthquake, which introduced by Professor Shahnaz Youssef, Astronomy, Space Science and Meteorology Department, Faculty of Science, Cairo University, and Dr. Rami Mawad, Astronomy and Meteorology Department, Faculty of Science, Azhar University in Egypt. Let me first give a brief definition of coronal mass ejection. Coronal mass ejection is an explosive outburst of solar wind plasma outward from the sun at speeds on order of hundreds of kilometers per second. There might only be one coronal mass ejection every week during solar minimum. When the sun's activity increases toward the solar maximum, coronal mass ejection become more common, and we can see multiple coronal mass ejection every day. The radiation storm, which are a part of coronal mass ejection, can be hazardous to spacecraft and astronauts. When charged particles from coronal mass ejection reach areas near Earth, they can trigger intense lights in the sky like called aurora. When particularly strong coronal mass ejection ejected from the sun, it also can interfere the power utility grids grid and which at their worst can cause electricity shortage and power outage. So it has been observed that sometimes there are green and blue lights appears in the sky during or just after severe earthquakes. We will present here 3 examples. Is it okay? Can you hear me, sir?
And now we can hear you. There was a little interruption,
Yes.
but
We can briefly talk about 3 examples. For example, that the blue and the green bright flash of light across Mexico accompanied the September 2017. In this time, there were proton flares. This proton flare was accompanied by coronal mass ejection and extremely strong X 9.3 class X-ray flare, as well as magnetic storm. Solar unusually solar
sorry,
particle.
I need to ask a question. The people in the audience can see the slides because I have a warning about sharing the screen. Do you see?
I can't see. I read from my slides.
Okay,
Not-
you see your. You can't see.
Yes, I can see
Oh,
my slides.
okay, maybe there was a problem. Now, do you see it?
Yes, we can see it.
Okay. So I think, Yasmin, you have a PowerPoint show, so I don't control it. It's transitions is automatic, right? Slide transitions.
Yes.
Okay. Now we have the green and blue. Okay.
Okay. I was talking about the solar particle event or solar proton event.
Okay.
It's occur when a particle emits by the sun. Mostly proton become accelerated either in the solar atmosphere during a solar flare or in the interplanetary space by coronal mass ejection shock. Nuclei such as helium may also be accelerated during this event. These particles can penetrate the Earth's magnetic field and cause partial ionization of the ionosphere. Here is a picture. This picture shows this green and blue lights which appeared in the earthquake. We talk about shapes earthquake. These proton flare, we suggest that they include the telluric electric current in the ground and in the magma. Thus cause motion and more subduction in the tectonic plates. Such motion immediately triggered the shapes earthquake in the near vicinity. The second example, which also earthquake show bright lights in the sky, is the 19th of September, moment magnitude 7.1. Babylon, central Mexico. It has been initiated by fast solar wind, coronal hole streams. Such streams, if they hit the ground, they cause earthquake. If they hit narrow seas like the Red Sea, they cause flash floods. However, if they target oceans, they initiate hurricanes. Very important that is the hurricanes Max made landfall in Guerrero State on 14 September near the earthquake-stricken region. Was initiated as low pressure area near the southwestern coast of Mexico in September. It was also initiated by proton stream. This confirms that when proton stream hits the ocean, they form low pressure areas as they heat the atmosphere by dissipating their energy there. As the air gets heated, it expands. So it form a low depression area. This process accelerates evaporation and that develop to hurricane. In case proton stream targets the ground and earthquake is triggered. The last example is the earthquake which happened in 7 September. Earthquake this year, 2021, which has been occurred in the moment magnitude 7.0 or 7.1. This earthquake has been occurred near the city of Abicalo in the Guerrero state of Mexico at 20:47 local time. This earthquake was severe and killed 13 people, and there was injured at least 23 other. It's remarkable, and we can Think about it, it has occurred in the anniversary of the first earthquake we have talked about in the presentation. The 2017 Shapes earthquake. There were a rare natural light show flash across the night sky during a powerful earthquake that shook Mexico City and beach resort late on Tuesday, adding to a sense of doom as Stride residents rushed into the street. Early in morning of September 6, 2021, the sun released two powerful solar flares. The second was the most powerful in more than a decade at 5:10 a.m. An X-class solar flare, the most powerful sunstorm category, blasted from a large sunspot on the sun's surface. The flare was the strongest since 2015 at X2.2, but it was dwarfed just 3 hours later. According to the National Oceanic and Atmospheric Administration Space Weather Prediction Center, during these, as we know, during a large solar flare like X-class solar flare, the sun can also send a cloud of energetic plasma from its body. Coronal mass ejection has been ejected. So we can say that, as a conclusion, the cause of the green and blue lights was the excitation of atmospheric oxygen and nitrogen atoms, similar to aurora lights mechanism. And how the proton flare can cause this earthquake. They produce electric current in the ground, in the magma. They move tectonic plates. How do these proton flares and solar wind cause hurricanes? Also, we know they heat the atmosphere, causing it to expand. This reduces its pressure at the boundary between the air and the sea surface. They just accelerate evaporation enormously, causing thick cloud in case of ocean interaction. They cause hurricanes in case of narrow sea, like the Red Sea. They cause flash floods, like Makkah Mukarrama, unpredictable flash floods. This is the end, and thank you.
Thank you, Yasmin. It was very.
I am sorry for the beginning, and I take much time from you. I'm sorry for this. For the beginning, the problem of the screen sharing. I'm sorry for this.
Okay, no problem. Thank you for the interesting talk.
Thank
but
you,
I have a question. I'm maybe it is lack of my knowledge, but I'm really surprised by your presentation. How is it a solid information, solid knowledge that the solar flares create tectonic movements, the earthquakes, or you are just making a?
We suggest that it caused telluric currents, and these telluric currents in the magma in the land cause the Earth's plates to move particularly.
But this is your suggestion. This is not proved, or
it is not. It's a point of research right now. Even in Romania, there are a group of research working on this topic, but no 100%. There is no result.
Because you didn't provide. Result, yes. Okay, but in such and just a suggestion, please take my the comment. But in such situation, I think you should provide some correlation between these events. So you just give some examples, but there is we didn't see any correlation in the frequency of these events. So I think it's very important to prove that things. And in your slides, you were talking like really explicitly, you are saying that it is like this, and so maybe you should rephrase your slides, because it's really surprising. It's very firm conclusion, I think.
Yes,
I don't know.
Thank you, sir, for your comment. But I think it maybe be very important to make more study about this. If the geometric solar storm make a severe earthquake, it will be It will be big useful for us to predict severe earthquake.
Okay,
Thank you, sir.
Shehnaz. Okay, Shehnaz raised your hand. Maybe do you want to talk? Yeah, probably it's just a coincidence, but Shehnaz, you can talk. Shahinaz. I love to talk, sorry. Okay, now you can talk. If you unmute yourself, you are muted. We don't see you, but...
Can you see now?
Yeah, perfect. We hear you now, please.
What should I say? What should I say here?
No, you raised your hand, so I thought that you wanted to talk.
Yes, I want to. Now you can hear me?
Yes, we can hear you.
All right. You see, one of my students got her MSc on the correlation between proton flare flares and very severe earthquakes. And it is found from statistics that proton flares initiate very, very strong earthquakes. And the general idea is that you get electric currents in the ionosphere, and these induce electric currents in the ground, and that moves the plate tectonics. However, this is a unique part where we have here when we see that the green lights appeared all over Mexico.
Mm-hmm.
And this is very strange. And what happens here is that, you know, usually the plasma gets through the polar points. However, in this case, they rushed over Mexico. And my explanation for this is that, you see, the direction of magnetic field of the solar wind at that time was Z negative. It's like when you have two magnets and you get the red and the blue together, and this opens a window in the magnetosphere where the protons get through to Mexico. This is a different case. And that is why my explanation is that it's directly moved. We have a picture here in the presentation, but you didn't see that actually, you see there is boundary between the plate boundary between the ocean plate and the Mexican plate. And what happened is that the Mexican plate gets underneath the ocean plate, and that triggered the earthquakes. And that is why I have suggested that this is a unique case. It's not like having the plasma getting through from the polar points.
Very interesting. I mean, I was really still surprised, because still amazed about that, because even after the magnetosphere, so what you are suggesting is that the proton flare are so strong that even after the prevention of the magnetosphere, it has some effects on the ground, and they penetrate from the ground. The electric current they create to penetrate from the ground to reach the magma and then affect their movements. They are
very, very energetic.
Yeah, but we're energetic, but we have a magnetosphere. So do you have some kind of competitions?
Through the window of the magnetosphere.
Yeah,
but they reach the ground.
Of course they reach, but I mean, what level? It's the question. Do you have any kind of computation that, for instance, what kind of electric current that needs to be created to move the tectonic plates for this kind of computations, because there's a massive event. So I mean the mass moving. In the presentation, I think I haven't seen them, but I mean, if later maybe we can discuss on that. It's very interesting. Thank you. Are there any other question from the audiences or comments in general for all the speakers? It can be as well, not just Yasmin, but any other speaker. Everybody is tired and they are leaving. Okay, so I think we can close the session. Thank you for all the speakers, all the contributors. So just one more time, I remind you that 6 p.m. UTC, there's a public talk which you can follow on the YouTube channel. That's all for now, I guess.
Well, I would like to say something, that I am interested in the history of Islamic astronomy, and I have taken part in making survey of all the scientific books in Cairo, and with the Smithsonian and David King, and we made a list of all the science and astronomical books, and it was a pleasure to have the opportunity to have all the ancient books in your hand and look at it. Thank you.
Thank you, Shahinas. So goodbye, everybody. Then I think if there's nothing to be said. Okay, so I leave the session. I thank everyone contributing for the organization. So
thank you, sir.
Have a nice evening. Seeing you tomorrow.
Thank you, Sinan, for sharing this session today.
Prego, Oscar. Prego. Ciao.